Every year, the world recycles over 630 million tons of scrap steel. To put it into perspective, if we collected all this steel, we could build over 60,000 Eiffel Towers every single year. But have you ever wondered what those rusty, dilapidated, seemingly discarded pieces of scrap iron become after emerging from a 1,000-degree furnace? They are not only reborn, but are undergoing a spectacular evolution to become stainless steel. The super-durable, gleaming stainless steel that is now found in every modern kitchen and future mega-construction. How does this journey unfold? That amazing secret will be revealed right here. But before we follow the journey of transforming scrap steel into stainless steel, there's an amazing fact that few people know. Unlike many other materials that gradually degrade after each recycling, steel can be melted down and reused almost indefinitely while retaining its essential properties. This means that the iron atoms inside a used car today may have once been part of a bridge, factory, or other structure decades ago. This exceptional recyclability also offers enormous environmental benefits. Recycling just 1 ton of steel can save the industry more than 2,400 pounds of iron ore, approximately 1,400 pounds of coal, and nearly 120 pounds of limestone. Resources that would otherwise have to be extracted from the earth using highly energy-intensive operations. This is also why modern metallurgical plants don't view scrap steel as waste. In their eyes, it's a pre-refined raw material with immense value that can be continuously recycled into new materials. And the steel recycling journey begins in the vast scrap yards scattered across the United States. Every day, thousands of trucks continuously arrive, carrying old cars, decommissioned industrial machinery, damaged shipping containers, and dismantled steel structures from construction sites. At first glance, it all looks like piles of worthless metal waiting to be discarded. But for the metallurgical industry, it is an extremely important source of raw materials. In the US, more than 10 million end-of-life cars are sent to recycling facilities each year, and about 95% of these are eventually recovered for reuse in various forms. The automotive recycling industry alone supplies about 12 million short tons of scrap steel to metallurgical plants annually. Thanks to this enormous supply, more than 70% of the steel produced in the US today comes from scrap steel rather than newly mined iron ore. However, during the collection process, the most important thing is not quantity but quality. Not all steel is the same, and even a small amount of impurities can affect the entire subsequent recycling process. Copper from electrical wires, motors, or electronic components is considered one of the most difficult impurities to handle. That's why modern collection sites are not simply places to dump scrap metal. They also serve as the first line of quality control for the entire steel recycling industry. After collection, scrap steel is sent to the baling stage. At this stage, most of the material is still too bulky to transport and handle efficiently. A car over 15 feet long or a 40-foot shipping container would take up a lot of space if left intact. To solve this problem, scrap yards use giant hydraulic balers capable of generating forces of up to thousands of tons. In just a few minutes, an intact car can be compressed into a much smaller, more compact block of steel. This volume reduction significantly saves storage space and transportation costs. At the same time, the uniform steel blocks are easier to unload and handle in subsequent stages. Even after being compacted, these steel blocks cannot go directly into the furnace. First, they need to be broken down and cleaned, and that's when the crushing process begins. In modern recycling plants, scrap steel is fed into giant industrial crushers with a capacity of up to hundreds of short tons per hour. Inside the machine, a rotor weighing tens of tons, fitted with high-strength alloy hammers, rotates at hundreds of revolutions per minute. After leaving the crusher, the material mixture falls onto a conveyor system to begin the automatic separation process. The first station is an electromagnet suspended above the conveyor belt. As the material passes, the magnet attracts all ferrous metals such as carbon steel and releases them onto a separate conveyor belt. The rest continues through a pneumatic system. High-speed airstreams are blown across the conveyor belt, carrying away lighter materials such as plastic, paper, foam, or fabric. Meanwhile, heavier materials such as metal fall to the bottom due to gravity. However, for stainless steel manufacturers, simply separating steel from waste isn't enough. They also need to know exactly which elements are present in each piece of metal. That's where X-ray sensor systems and alloy analyzers come in. As metal pieces pass through the scanner, X-rays penetrate the material and measure the chemical reaction of each element. In just a few milliseconds, the system can determine whether it's ordinary carbon steel, whether it's 304 stainless steel containing about 18% chromium and 8% nickel, or whether it's 316 stainless steel with added molybdenum. However, even the most modern sorting systems cannot completely eliminate all impurities. That's why, before being sent to the furnace, the material stream must undergo a final manual inspection. Along conveyor belts tens of feet long, workers continuously observe and remove unwanted remaining objects such as rubber, hard plastic, wires, batteries, pressure vessels, or unsuitable metal pieces. Thanks to this series of sorting steps, the initial piles of mixed scrap are gradually transformed into much cleaner and more uniform streams of raw materials. After passing through a series of crushing, cleaning, and quality control steps, scrap steel is finally ready to enter the most crucial stage of the entire recycling process, melting. Its destination is the electric arc furnace. This is the heart of most steel recycling plants in the United States. A typical furnace can process from 70 to over 200 short tons of steel per batch, and many plants operate dozens of batches continuously each day to meet production demands. When operation begins, the furnace roof opens to allow the scrap steel to be loaded inside. Then, 3 enormous graphite electrodes slowly descend. Currents of up to tens of thousands of amperes are passed through the electrodes, creating extremely powerful electric arcs with temperatures that can exceed 5,000 degrees Fahrenheit. Under that intense heat, blocks of steel that were once cars, machinery, or construction materials begin to melt and merge into a massive pool of molten metal. A single smelting batch typically lasts from 30 to 60 minutes, depending on the amount of raw materials and the technology of each plant. Throughout this process, pure oxygen is continuously blown into the furnace to burn off excess carbon and remaining impurities. Simultaneously, limestone and dolomite are added to absorb unwanted components, forming a layer of slag floating on the surface of the molten steel. When the process is complete, hundreds of short tons of the initial mixed scrap metal have been transformed into a glowing orange-white pool of molten steel. But at this point, it is still just ordinary recycled steel. To transform that molten metal into stainless steel, the plants must perform a crucial next refining step. After leaving the electric arc furnace, molten steel is not yet stainless steel because its chemical composition does not yet meet the stringent requirements of stainless steel. That's why the molten steel is transferred to a special device called an AOD converter, short for argon-oxygen decarburization. From the outside, the AOD looks like a giant steel vessel that can hold tens to hundreds of short tons of molten metal. When the process begins, a mixture of oxygen and argon gas is blown into the molten steel through nozzles located at the bottom of the furnace. This allows carbon to be reduced to extremely low levels while most of the chromium is retained. This process typically lasts from 45 to 90 minutes, depending on the type of stainless steel being produced. The main goal of this step is to remove carbon without losing chromium, the crucial element that gives stainless steel its corrosion resistance. Once the carbon content meets the requirements, engineers begin adding precisely the necessary alloying elements such as chromium, nickel, and sometimes molybdenum to increase corrosion resistance. After completing the refining process in the AOD converter, the molten stainless steel now possesses the precise chemical composition required. However, it is still just a liquid metal slurry with a temperature of up to approximately 3,000 degrees Fahrenheit. To become a raw material for later production plants, the stainless steel must be transferred to the continuous casting process. Here, the molten stainless steel is poured from the refining furnace into a giant container called a ladle. A large ladle can hold from 100 to over 300 short tons of molten metal. From this container, the stainless steel continues to flow into an intermediate tank called a tundish before being evenly distributed into water-cooled copper casting molds. Upon contact with the mold walls, the outer layer of metal begins to solidify almost immediately, while the inner core remains in a liquid state. And instead of casting into large ingots that must be reheated as before, the molten stainless steel is directly transformed into ingots hundreds of feet long. When stainless steel billets leave the casting system, they are still glowing red and have temperatures exceeding 1,800 degrees Fahrenheit. Instead of letting them cool completely and then reheating them, factories utilize the enormous residual heat to directly feed the billets into the hot rolling process. Upon entering the line, the stainless steel billets pass through a series of massive rolling stands. Each stand consists of 2 or more high-strength steel rollers capable of generating forces of up to thousands of tons. Under this immense pressure, the stainless steel billets are gradually elongated and reduced in thickness with each pass through the rollers. A slab several inches thick can be rolled down to a fraction of its original size. Meanwhile, its length continuously increases, sometimes reaching hundreds of feet before the end of the line. Upon leaving the hot rolling line, the stainless steel can appear as giant coils weighing tens of short tons or long sheets of steel used in construction and industry. Looking back at this entire journey, perhaps the most amazing thing is that it all started from seemingly worthless piles of scrap metal. Old cars, broken machinery, or structures that had reached the end of their lifespan were collected, crushed, cleaned, melted, and refined to become new stainless steel, one of the most durable and important materials in the modern world. If you enjoy stories about the engineering, technology, and manufacturing processes behind everyday objects, don't forget to leave a comment, hit the like button, and subscribe to the Mido Explained channel so you don't miss the next videos.